Now this is the new lecture in which we are trying to find the torque on a dipole when it is placed in a uniform electrical field. We have done two derivations previously in which we have find out the electrical field due to dipole on both the lines. Over here we are trying to find the torque or force on electrical field when it is kept in a uniform field created by some other source, some external field, right? Okay. We'll try to study the torque on dipole in uniform electrical field. You can see in the diagram we have got two point charges plus q minus q placed two distance apart. The direction of electrical field is towards the right side. Now this is the direction of electrical field and hence the force on the positive charge is towards plus QE. Force on negative charges QE. You see, because of minus sign we have got this thing is minus QE. In a vector, minus means opposite direction. So since it is uniform field, the force on the plus QE and the force on minus QE both are equated. So there is no net force on the dipole. But since the QE force on this and the QE over here, they try to tend to rotate the dipole. So we will study the effect of that. That's what is called the torque on a dipole. See, the torque on a dipole when it's already at an angle theta, we have seen, supposing I take the moment about this minus charge. So the force is QE. Now force into perpendicular distance would be the torque. 2a is the distance and 2a sin theta becomes a perpendicular distance. So electrical torque on dipole will be force into 2a sin theta. You know force is QE. We multiply by 2a sin theta. We gives it 2 QE a sin theta. Remember 2QA is P electrical dipole moment. So we place the value. And since A cross B is AB sin theta, in a vectorial direction we can write torque is P cross E. And in scalarly we write torque is PE sin theta. Remember, whenever the angle is 90 degree, sin theta becomes 1 and the torque is maximum. That's the maximum value of any sin theta. And whenever the angles are 0 or 180 degrees, the sin theta is 0 and hence torque becomes 0. Now second thing is, we apply some force, some torque is there, obviously some energy might be stored. So let's try to find the potential energy of a dipole when it is placed in a uniform field. Now potential energy is basically calculated by doing the work. Whatever work is done in making a system, that has to be sent as a potential energy. In linear forces, the work done is given as F dot x, that is force into displacement. But over here, since the torque is being applied, we call torque into d theta. And since torque is not constant, we'll have to take the integration. Similarly to situation when the force is not constant, we take f dx rather than f delta x. We take integral of f dx. Here we'll take the integral of torque and theta. Now u is torque d theta. Torque is given as PE sin theta. We have just now calculated it. It's PE sin theta d theta. You know very well the integral of sin theta is minus cos theta. I place the value, it becomes minus b cos theta. And I remember a dot b is ab cos theta. So in a vectorial direction, we can also write minus p dot e. Energy being a scalar does not have any direction but does have a magnitude. Now again, we try to study at theta 90 there is no potential energy. But force was 0 at two places where theta is 0 and theta is 180 degree. When theta is 0, my potential energy becomes minus PE, which is the least. And when theta becomes 180, though the force is non-zero, so sorry, the force is 0, but the potential energy becomes plus PE, which is the highest one. That we mean to say that despite of being no force at 0 and 180, the potential energy in these two cases is not the same. At 180 degrees, the potential energy is higher, and at 0 degree potential energy is least. Now we talk of uniform field, the force is always 0. The torque is 0 at 0 and 180 degrees. Actually we are trying to find the equilibrium position. Though for equilibrium there should be no force, no torque. So whenever you place a dipole in uniform electric field, the force is always bound to be 0. We go to second place where the torque should be 0. The torque is 0 at theta equal to 0 and 180. Now the question is, which is the stable equilibrium? The definition for the stable will be when you have a lower energy, and when you have a higher energy, it's unstable. We see P is stable at 0 degree, is less at 0 degree, minus P, and at 180 degree is plus PE, which is more. Hence, the stable equilibrium is at 0 degree and unstable at 180 degrees. In the next video, we'll talk of the certain other aspects. For other online courses, you can join me or contact me at my email. Hope you have understood the concept and this is completed to you. Thank you.